x squared. So you place that right here. And then you're actually going to multiply x squared times this. And sometimes I'll write it down on the side. I'm multiplying x squared times x minus 1, which distributes to each one I get x cubed minus x squared. Right? That's what's happening. I'm going to multiply this times this. And that gives me this. And now I'm going to put those underneath, and I'm going to line them up properly. So x cubed goes under x cubed. And then minus x squared goes under this x squared. What I'm doing, believe it or not, I don't know if you recognize this. If you were doing like 12 divided by 4, no, let's go 13 divided by 4, then you would go 13, 4, right? Then you say 4, 3 here? Then 3 times 4 is 12, and then you come through and you subtract and you have 1, right? That's what we're doing, basically. So I need to still come through here and subtract. So when I subtract, it becomes minus, then plus. And go ahead and add down. Tell me what happens when you add that down. X squared plus x. No x squared, it's plus x squared is x squared. X plus nothing is x. And then we play the game again. X times what gives you x squared? X, so I put x here. And then again, I can do it over here. It's x times x minus 1. That's x squared minus x. Put that underneath here. So x squared minus x over subtract. What happens when I subtract there? I get minus here, and this one changes to a plus, doesn't it? Didn't that happen here also? I didn't really stress it, but that happened also. That minus changed to a plus. Add down. 2x. Play again. Can you turn x into 2x? Multiply by 2, right? So plus 2 here. And I'm kind of running out of room, so let me get rid of this. So I'm doing 2 times x minus 1. That's 2x minus 2. I put that underneath, right? 2x minus 2. I come through. I subtract. It changes the signs. Got minus, and this goes to plus. Add down, 2. Turn x into 2. So that's not going to happen, right? That's when you stop. So what do I put up here? R2. R2, okay. That's what we did. That's what we would do back like in the day, right? Way back in the day.
So this is going to be plus
What we do is plus
2 over x minus
the remainder 2 over the divisor x minus 1. R2, yeah, that's good old days.
Hey son, what'd you learn in calculus today?
We did remainder 3. Everyone got that? Your remainder over your divisor is the last term. So think about what we've done here. It's like when I say 15 over 5 is equal to 3, I'm saying that this expression is the same as this expression, right? So when I say this division turns out to be this, that means this expression is equivalent to that expression, right? So I'm going to rewrite this integral now. All that long division was to be able to do this. Rewrite it as x squared plus x plus 2 plus 2 times x minus 1. Pardon? Can't we do what? Split them up? Absolutely. Things are really going to be nice here. Because when we look at that, we have a bunch of separated terms, and we can integrate them term by term. What's the antiderivative of x squared? 1/3 x cubed. What's the antiderivative of x? 1/2 x squared. Good old days, right? Antiderivative of 2, 2x. Antiderivative of this, 2 natural log. Absolute value, x minus 1 plus c. So the only one here that should have been maybe a little bit troubling to you was this one, but that's constant over linear, and that was the first example we did today, right? Constant over linear. Goes right to that. We're done. This required no partial fraction decomposition, none at all. This was just, hey, long division, everything worked out nice, we're happy. Life's good. That example was really just to get you familiar with long division again. I lied to you. I forgot. There was one more example I wanted to do. This will be our last one, I promise. You cannot complete the square because the bottom is not a square, right? It's cubic, and so we don't really have a technique for like completing the square with that. Completing the cube, well, the question is, what would you want it to look like? I don't believe there is. But even if we did, it wouldn't help us. Okay, so you sit there and you're like, well, this is obviously a rational function, right? Polynomial divided by a polynomial. The degree of the numerator is 2. Degree of denominator is 3. Yeah? Therefore, no long division. So we move on to step 2. Step 2 is where partial fractions comes in from pre-cal. Now I could sit here and read this to you, but it's really ugly to read initially. It's better to go back and read it after we do an example. So what I'm going to do instead here is just take you through the technique of partial fraction decomposition. What we do to start is write down the integrand. Forget that we're even doing an integral right now, okay? My goal, if at all possible, is to see if there's any way I can rewrite this where it's separate terms. If I can somehow rewrite this as separate terms, then maybe I can integrate each one of those separately and it'll be easier. Maybe. If there's any justice in the world, maybe it can happen. So I will initiate the partial fraction decomposition by trying to completely factor the denominator. So you get to factor. So factor out that denominator for me. Notice anything? You can factor an x out. Okay, so that's a GCF. That's what we call that back in college algebra. A greatest common factor. And then can you go any further? Can you factor this quadratic, or is it irreducible? So let me just be very honest with you. You have to be able to do this, okay? I mean, at this point, we're in Cal 2, so you've got to be able to factor a trinomial. So if you've got some method that you learned in college algebra, you need to break that out here to here. You all okay? Yes? And if you want some help, you can come by my office if you forgot how to factor. Do we agree with that? Okay. Now the partial fractions, which again I've stressed to you. Since this is a pre-cal topic, I'm gonna show it to you, and I want you hopefully to remember some of this. Let me just bring this up here. What we're gonna look at here is the fact that what we have in the denominator are what we call 3 distinct linear factors. Each of these individually is linear, right? X is linear, 2x minus 1, linear, x plus 2, that's linear. They are distinct, meaning that they are not the same, right? This is x, this is 2x minus 1, this is x plus 2. If 2 of these were x plus 2, then you would have a repeated linear factor, which requires a completely different approach. So our first example, where we're having to use partial fractions, we have distinct linear factors. And if we scroll back up to the steps, it says here, case 1, denominator has n distinct linear factors. Then this is what we do. But forget all that. Let's just do it. So from pre-cal, what we realize is that this is going to become 3 fractions. The first fraction will have x in its denominator, the second one 2x minus 1, and the last one x plus 2. Partial fraction decomposition tells us that this does break apart into those 3 fractions added together. The only thing we have left to resolve are what are the numerators. And these will always be some numbers, a, b, and c. And we now need to figure out what a, b, and c are. And if we can figure it out, do you agree we'll be in business? Because just imagine that, just for the sake of making this really easy, just imagine that this was 1, 1, and 1. Could you integrate each of these individually? Absolutely. You'd have constant over linear, constant over linear, constant over linear. We're done. So can we get these 3 things? See, back in pre-cal, when you're learning partial fraction decomposition, they don't tell you the reason why you want to go from here to here is because later on you need to integrate it. And integrating that is not easy. Integrating these individually is easy. So it was all for this purpose. Yeah, so how do we find a, b, and c? We take this equation, we clear the fractions. We multiply both sides by the denominator over here. So I'll do it in blue. We're going to take the entire denominator, x times 2x minus 1 times x plus 2. We're going to multiply it on this side and on this side. And we do it on this side, it has to go to each term, doesn't it? So I'm going to squeeze that in here. X, 2x minus 1, x plus 2, x, 2x minus 1, x plus 2. This one, x, 2x minus 1, x plus 2. Now, you don't always have to show this step, and I will stop showing this step at some point. But that's what's actually happening algebraically. We're clearing fractions. Now, what happens on the left side is that this all goes away, and all that's left is the numerator, right? On the right side, certain things should cancel out. So we should get, in this one, the x's will go away, right? Here the 2x minus 1 will go away, and here the x plus 2 will go away. So we should have no more fractions, right? We should just have the a times the 2x minus 1, and then times the x plus 2, plus bx times x plus 2, and finally c x times 2x minus 1. Everyone clear on what I just did? Now there are 2 methods that we can use to proceed from here. There are 2 techniques. One of them is the shortcut, the other one is the long way. The shortcut is definitely preferred, but it doesn't always work. The long way will always work. Yeah. Yeah, that's the short way. So what I'm going to do is today I'm going to do the short way. And when we come back next class, I'll finish off this problem with the long way. So you can see the 2 methods. So short method. Which is preferred, but like I said, it does fail to work sometimes. The short method is to try and see if there's any way you can figure out what A, B, and C are one at a time. So maybe there's a way that I can figure out what A is. And to do that, I'm going to try and kill off B and C. So can you give me a value of x that would kill off this term and this term? 0. If x was 0, that would go away. X 0 here, that would go away. But x being 0 here does not kill it off, right? So that's what I do. I get a little bit of what we call a God complex. This is one of the few times in math that you have control, okay? You get to let x be whatever you want. So I'm going to let x be 0. You can use the voice, you know, it's kind of that, let x be 0. And now you get to see what happens. So rewrite the entire equation, replacing all x's with zeros. Gone, gone, -1, equals a 0 minus 1, -1, 0 plus 2, 2. And then this was 0, that's gone. This was 0, that's gone. Yeah? So the only thing left is that little equation right there, which is really saying -1 equals -2a, which means a is a half. Okay. Good. Can you get b doing a similar thing? Let x be. So we want to kill off this one and this one, right? These two. So what you're going to look for is what factor do these two have in common? 2x minus 1. How can you make 2x minus 1 equal 0? Yeah, just solve that little equation. X is a half. If x is a half, that'll go away, right? So let x be a half. Does any of this look familiar from pre-cal? All right. So x is a half. Let's plug in a half here. A half squared. Was it a half? Yes. X is a half. 1/4, right? 1/4 plus 2 times a half. 1 minus 1. That's the left side of the equation with my x's replaced with 1/2. So that's just going to be 1/4. This one's gone, right? This one's gone. This one's not. This is b times a half times a half plus 2. 5 halves. Left side, 1/4. B times 5/4. Right, so put those together, multiply 5/4. Multiply by the reciprocal, 4/20, which is 1/5. B is 1/5. Now what? Oh yeah, you could, but I mean, we may as well stick to what's working, right? I mean, we could do this again for C. Can you kill these two off? What are you going to let x be? -2. May as well just continue with the method. I agree, you could go and solve it, but I'm not going to abandon what's working here. -2 here. -2 squared, 4. What's 2 times -2? -4, so -4, -1. So that's your left side. This is gone, this is gone, this is not gone. So C times 2 times, no, -2, right? -2. And then -2 times 2 is -4 minus 5? Left side, -1. Right side, 10C. Where are you getting that from? Yeah, these 4's cancel, and you get -1. So -1, and then -2 times -5, 10. C is -1/10. There we go. I've got 1 minute. I'm going to finish the problem. So this integral up here becomes, and you got to remember what A was over, B was over, and what C was over. This integral becomes integral of A over 1/2 over x plus B, which was 1/5 over, what was the second factor? 2x minus 1. And then finally plus c, which was negative 1/10 over x plus 2 dx, right? So I have partial fraction decomposition on this integrand. It turns into this. And now I'll peel out constants, and I'll be there. Okay. I know I'm out of time. This is 1/2 integral 1 over x dx plus 1/5 integral 1 over 2x minus 1 dx minus 1/10 integral 1 over x plus 2 dx. So just taking all those constants and popping them out of the integrals. That fair? And now just integrate these. These are all constants over linears. 1/2 ln x, absolute value, plus, this one's a little tricky, 1/5, but then 1/2 ln 2x. You have to scale out because there's a 2 here. And then last one, minus 1/10 ln of x plus 2 plus c. I forgot to take attendance. Is everybody here? Who's not here? All right, so for your homework, I don't have it. Did I list it on here? I think I did. I think I came back and listed it. Okay, here's the homework. It's page 344. It's 7 through 41 odd, but I know for a fact you can't do all those yet. So anyone have the book with them or no? Nobody? Well, I want to, yeah, here we go. I can tell you real quick which ones of these you can do right now based on what we did in class today. Based on what we did, you should be able to handle 7, 9, 11, 13, 17. Yeah, that's good. Those are 5 problems where all of them are going to be distinct linear factors, and you do it the same way that I did there. Remember, my homework solution videos will cover this. We will come back. I'll do the long method. Remind me, that's what we're going to start with. Long method on that, and then we'll do some more problems. There is a very high probability of a quiz on Thursday.